Hi everyone, welcome to these Python tutorials where we are putting special emphasis on image processing related tasks. We started our discussions about deep learning a couple of tutorials ago. And before we get to the stage where we have all the skills to put together our own deep learning models for specific applications, we need to understand various terminology. And this is the first of those tutorials where we start by understanding scaling, and in the next one we'll talk about activation function and so on. And let's spend a few tutorials talking about the basics, because these are very important tasks or parameters that you're going to tune. When I say task, this can be pre-processing tasks. For example, scaling. How do you handle your data before it goes into the neural network? When it comes to the next video, activation function, which activation do you pick when you're putting together your neural network? For that, you need to understand what activation is. For this, you need to understand what we mean by scaling and what options do we have at our disposal when it comes to scaling. First of all, let's see the need for scaling and then many ways of doing this scaling. So scaling and normalization are usually used interchangeably. In some cases, they can be the same, but scaling is an important machine learning task. I'll talk about normalization in a minute, which is, in my view, a way of scaling your data. But scaling is important because the models can be sensitive to magnitude of features. Not all models, but especially deep learning models can be sensitive to the magnitude of features. What do we mean by that? If you're trying to put together a model where you're trying to see, okay, based on the age group and the price of the housing at a given location, what is the probability of someone purchasing a house of certain value, right? I mean, I'm just giving you an example that all of us can relate to. Now, in that case, the age goes from 0 to 100. In reality, the people who are purchasing the houses, probably the range goes from 20 to 60 or so. But when it comes to house prices, depending on the location, it can go from 50,000 to 100,000 to like a few $1 million, right? So this is a 2-3 orders of 4 or 5 orders of difference in magnitude. So when you have this much difference, then neural networks can struggle to converge. Okay, so that's the first thought. That's the reason why you need to scale everything so all the values can be represented in a similar scale. Now, scaling your features, in some cases you can call it attributes, right? If you're looking at perimeter or area of certain cells, these are the attributes, typically referred to as attributes. But in general, your features are attributes. This is one of the most critical steps that you have to perform in pre-processing the data. Otherwise, sometimes you'll realize that why is my loss not improving anymore? Maybe scaling is the reason, maybe. And if you look at what we mean by scaling, it's basically bringing all the values to some uniform scale, whether the values are between 0 and 1 or -1 and 1, just to bring all the values from all the attributes into a similar range so they can be easily comparable. For example, if the age is 100, then age can go from 0 to 1 if you divide everything by 100. If the maximum value of a house price is 1 million, then you can just divide your house prices by 1 million, and then you can just go from 0 to 1, right? Both are in the same range now, age and house prices. The example I just gave you is one specific form of scaling. Again, we'll see a few forms in a minute. Now, the term normalization is used when you want to bound your values between numbers like, okay, typically 0 to 1 and -1 to 1, where, again, there are different types of normalizations where you have your center, like mean centered at 0. There is something mean, So this is the term normalization. Again, I know most of you are probably non-statistical background people, like most of you are probably biologists or material scientists or geologists. So let's not get into statistics here. Let's use statistics as tools. I'm just giving you an idea in terms of what tools exist out there so you can use them. Okay. Although it's very important, if you're designing experiments, you need to know statistics. That's a different topic. Now, here is a quote from one of the original papers. Having features on a similar scale can help the gradient descent converge more quickly towards the minima. What do we mean by that? Well, gradient descent, again, one of the tutorials in the next 2, 3, 4, we are going to talk about backpropagation and gradient descent. This is the meat of how neural networks actually work. So gradient descent is an algorithm that's trying to help the model converge. Okay, or find the convergence point for this model. So for that to actually get to the answer in a quick way, having all the inputs in a similar scale can definitely help. Now, when do you need to scale your features? It's not like you have to scale your features all the time, but when do you need to scale the features? Well, algorithms that rely on distance measurement. For example, if you're looking at k-means, of course it does matter, because you're looking at numbers that have completely different magnitude. So if you just run k-means, it may be skewed towards one set or the other, or principal component analysis. So this is when you need to scale. We are, of course, talking about deep learning. So in this case, because we are going to use a variation, either direct gradient descent or a variation of gradient descent, it's very important in this case. Why? Because it helps the problem to solve, to converge in a very fast way. Why? Because gradient descents faster on smaller ranges. Now think of gradient descent as you're trying to come down a hill and trying to find out where the bottom of the hill is. Now if that hill is very shallow and versus very steep, now you know how fast or how the problem converges and all that. But now think about this hill having a range from in the values of 0 to 1 versus 0 to 1 million, right? So the model doesn't seem to converge fast enough when one feature has smaller range, the other feature has a large range. Now it has to figure out how to balance these two. Okay, so this is again, we'll get into gradient descent later on, but just to give you a reason why scaling is important, because we can help gradient descent actually find that minima faster in a decent amount of time. And you do not need to scale these, because we haven't talked much about scaling in when we were talking about random forest or XGBoost or light gradient boosting, primarily because these are rule-based. Right? We are splitting various features in a random way for random forest, and we are trying to split them further, and we are trying to just go by rules. Hey, is this greater than this or less than that, right? And for each feature, we are doing this as a rule-based, so you don't need to scale your values when it comes to these rule-based algorithms. So that's a quick overview. Now, when it comes to images, like oftentimes we talk about image classification and semantic segmentation and everything, scaling can be very easy, because if you work with 8-bit images, the values go from 0 to 255. And it's only one attribute that we're talking about. When a pixel value, which is the one attribute we're talking about. So how do you scale those? You just divide your pixel value by 255 to get a value between 0 to 1. You're all set. Okay, you don't need any fancy way of scaling. If you want to scale your values between -1 and 1, then you can definitely, you know how to do that. It's a pretty easy. What is half of 255? 127.5. So image minus your pixel value minus 127.5 divided by 127.5. This squeezes your values to between -1 and 1. So for images, scaling is very easy. Just divide by 255. I do this all the time, just by 255. Okay. Now for other attributes, where you have like many other attributes. One of the examples we saw earlier was, for example, Wisconsin breast cancer data set. The area has one value, the perimeter has a different value, and then something else, brightness has a different value, and so on, right? So you have many attributes with different ranges. There, it's very important for us to scale. Now let's jump on to our Colab notebook to have a quick look at various scalings that are very common, and get a good understanding of what do we mean by, for example, MinMax Scalar. How does it look like? Okay, so let's spend a few minutes talking about that. I'll share the notebook. Please have a look at the direct link under the description down below in this video. So here is the notebook, again, as I said, I'll share this, and I should remind you to sign up to appear.com, because we have machine learning toolkit there. If you would like to use UNet, for example, for your image segmentation, all of that, we have the tools. All you need to do is annotate your images, train them, and segment them. Okay, and it's free. That's why I'm promoting it here. Okay, now going down, let's go ahead and import some data. Again, I try to stay away from describing this line by line, but it looks like I end up talking about these line by line. But let's go ahead and import the useful libraries there. Again, all of these are pretty straightforward. And now let's go ahead and read the file and print out the head. I connected my Google Drive account, so I'm reading this file directly from my Google Drive, and we have done this in the past. At least once. So this file, again, I'm printing out the head, as you can see, the top 5 rows, and the first column is ID, the second column is diagnosis, is it like a malignant or benign, and then you have like a whole bunch of other values here, which are not really visible just by printing. So let's go ahead and print what columns do we actually have. So these are all the columns, these many attributes or parameters, and each of these have different ranges. Now let's look at the distribution plot in terms of only radius mean. Let's pick only radius mean here. Okay, just look at the data. You see the data went from 0 to about 25 or 30, I should say. That's a decent range. And in fact, let's plot 3 of these. That's just one plot. You can play with individual attributes, but let's plot 3 of these. One is radius, the other one is area, the one is smoothness metric. Okay, so the radius is going from, as we just saw, 0 to 30-ish, and the area 0 to 2500, and smoothness is between 0 to 0.03 or 0.04. Different ranges. I know area and radius are related in this case, obviously. This is a square relationship, but smoothness is completely at a different scale. Okay. Now let's look at this data set and see how the ranges are. So my data frame.describe is going to give me all the information. So I have 569 data points, and my radius is around 14 is the mean value. And you can see the percentile, 75th percentile, and then maximum right there. And then you can see some of these are 1,000th of 7. In this case, the smoothness, we just saw that the smoothness has very small values, and so on. So how can we normalize these? Okay, let's actually normalize these in a few ways and then visualize the results. So let's focus on a couple of attributes instead of all of these. So first of all, for X, let's go ahead and drop the diagnosis and ID axis, right? This is how we actually define our X values. And let's plot our area mean and smoothness. Okay, these are the 2 we are going to focus from now on. So my X is basically the data that normally goes into our machine learning program, right? And Y is diagnosis, because this is what we are trying to predict. So from within X, I'm only looking at area mean and smoothness. I'm plotting area mean on X-axis and smoothness on Y-axis to have a quick look at how the data is spread around. Okay, so again, visually we can say that our area is going from 0 to 2500-ish, and our smoothness is going from 0 to 0.03. Okay, so this is a good understanding. Now let's get into how can we normalize these 2, and then just quick visualization in terms of what happens when we normalize it or scale it using a specific type of approach. So the most common way of scaling are the ones I'm just showing you here. In fact, the most common are MinMax Scalar. Obviously, as you can see, it scales the values between minimum and maximum in that data set. And max absolute scalar is the other one. Standard scalar is another one that's most common. I do not use robust scalar or quantile transformer, even normalizer much. MinMax Scalar is the one I use quite often. And I think not just I, but most people prefer, I've seen most code out there using MinMax Scalar. Okay, why? First of all, what it is, it transforms features by scaling each feature to a given range. Okay, and now let's come down here and look at this. So the way you implement this is, first of all, these are all part of scikit-learn pre-processing. Okay, so from there we imported all of these. Now I can just use MinMax Scalar, right? So I created an object for MinMax Scalar, and I'm not providing any range right now, which means it's using the default ranges, which is 0 to 1. Again, all MinMax is doing is it scales features to a given range. And in this case, the given range is 0 to 1. So it takes all the values and scales it between 0 to 1. And how do we apply that? The bottom part here is just plotting. So the way you scale something is min-max scaled x is your data frame and fit all your x values. And this is pretty simple, as you can see. You just start or create an object for min-max scalar, and then you fit it to your x values. So there are two ways. You can first fit and then transform. You fit to your x and then you transform all your x values. Or if you just want to minimize the lines of your code, you just use fit transform instead of fit and then transform as two different steps. That's all we are trying to do. Okay, so I'm fitting and transforming my x right there. And this is my min-max scaled x. And this is exactly what we are going to do for standard scalar and every other form of scaling. So using this in Python is very easy. Let's understand what it means by plotting them. So all I'm doing is applying this and plotting this for area, mean, and smoothness, right? These are the two. And I'm plotting before and after scaling. So let's go ahead and do that. Obviously, we need to run this line if I haven't already done so. And then let's go ahead and plot it. Okay, so on the left-hand side is the original, and on the right-hand side is after scaling. As you can see, original is going from 0 to 2500 or so, and 0 to 0.03. But after scaling, it goes from 0 to 1 for your area mean and 0 to 1 for your smoothness. So actual data itself didn't change. You see the structure of the data, the outliers, everything is there. Okay, so that's the reason I like min-max scaling. The values of each data point are between 0 to 1. That's what I like about min-max scalar. It's not changing the actual data itself in any way. It's not moving it. It's not moving the mean. It's not moving the variance, nothing. Statistically speaking, these two data sets are identical. It's just that we scaled individual values. That's why this is the most preferred way. Now you can actually change the values between, I don't know, if you don't like 0 to 1, you can actually put -1 and 1. And now the values will be scaled. Not sure what's going on there. Let's see. Int object is not subscriptable. Oh, sorry. Always do this mistake. Okay, there you go. So that should definitely fix that issue. And now let's look at the values. Now instead of between 0 to 1, you can see -1 to 1 and -1 to 1. That's it. So min-max scalar is take your range of values and fit them between certain range. Now standard scalar, anytime you see the term standard, that means it's doing something with the mean. Okay, so standardization refers to centering the data around 0 mean. That's what the standard scalar actually does. And here is the equation, and you can go ahead and read these at your leisure. So I copied all the documentation from the original documentation, so you can read through that. But again, the implementation is very similar to what we saw earlier. Again, the data doesn't seem to be changing. Again, the mean is centered around 0 for this one. So the values are not going from 0 to 1 or -1 to 1, but the mean is of focus right here. It is actually centered around 0. So you see the mean, if you draw a line right here, the mean is centered around 0. Here, if you draw the line around the center of gravity, the mean is centered around 0. But the values are going from -1 to 5 here, -2 to 8 here. Again, this is one way of scaling. And max absolute scalar, I should admit I have never used it, but I just want to demonstrate what it is. Again, scale each feature by its maximum value. Okay, let's have a quick look at how it looks. They all should look very similar. Again, this one is going from 0 to 1, and this one also going from 0 to 1. This looks very close to min-max scalar to me, because they are all scaling to absolute value, and apparently in these cases the minimum value is 0. Okay, now normalizer, again, another way. So let's go ahead, and normalizer we can provide, like for example in this case we are providing like L1 or L2 or maximum in terms of normalization, and you can see it is kind of moving our data. Again, if this is of interest to you, please go back and read the documentation. Yeah, again, these are all the terms directly from statistics in terms of how you deal with your distribution of data and how you properly process those. Okay, now if you change this from L1 to L2 regularization, for example, then the distribution probably slightly changes. I have, again, disclaimer, never ever felt the need to use anything other than MinMax Scalar or just dividing my images by 255, but there's a reason why these things exist. So this is your data. Obviously, the structure of the data itself is changing, as you can see, when it comes to how it's distributed. Now let's get into a bit more complicated type of transformations. This is Quantile Transformer. Again, it's transform the features to follow a uniform or a normal distribution. Okay, so hopefully we can see that as part of our plotting. Yeah, you see what is a uniform or normal distribution, right? So it's almost like a Gaussian bell type of distribution there. So it's taking your input data and actually transforming it into a normal distribution in both obviously all the attributes. We are only looking at area, mean, and smoothness. So it's actually covering the entire range from 0 to 1 and 0 to 1. That scares me a bit when my input data is changed by this much. So in summary, let's go ahead and plot all of these so we can get a quick snapshot of what we have discussed. So this is your original data right here when you only look at smoothness. Okay, let's just look at smoothness. So here is your original data, and here it is min-max scaled, and we are scaling it between -1 to 1. Remember, we changed it from 0 to 1 to -1 to 1. And again, the reason why I recommend this is because the actual structure of your data is not changed. Standard scaled is also very similar, except you see how it is centered around 0. Okay. And when it comes to these other ones like normalized or max apps and quantile, it's again, depending on the need, you can think about which one fits better, but assuming you're all working with image processing related tasks or typical structured data, not getting into financial analysis and all that. Like I said, the min-max scaling is probably all you need to know about. Okay, so I hope this provides a nice overview of scaling. Why do we need scaling? Hopefully is clear. And what type of scaling tools do you have at your disposal, and why do we often pick min-max scaling? I hope these are clear. If so, you probably understood the core essence of this tutorial. If not, please leave any questions in the comment section. Please do like this and then subscribe these videos. In the next tutorial, let's talk about activation functions. Please stay tuned.